Okay, sorry for late start. Oh. Okay, any questions so far? Sorry, it's a bit messy here. I just recorded it that we have this extra section I should fill up, and it takes a bit longer than I think. So let's try to do this on the fly. Okay. So anyway, yeah. After I thought a little more about partial trace, I found out that there were something. I guess you can really derive this, but we should talk about this more explicit. Okay, so let's go back a little bit. So go back from our classical computation to quantum mechanics. So let's talk a little more about partial trace. Okay. So remember we defined partial trace with this definition. So we say it's defined by these two properties. First is that if your if your density matrix is a tensor part of two density matrix, then partial trace is just you take a trace on the second part, and and it become a matrix on the first part. Okay, so the second part you trace it, and they become number, and also by linearity. Okay, and then I realized there are two important properties about partial trace that obviously you can derive from those two properties, but this will let you feel that why this is partial trace. So first property is that it's a very computational property. So it's an extension of the property of trace. So usual trace, we know it's a sum of diagonals, right? So trace there are, okay. So if you have a trace any matrix, so trace A then equal to summation I, and then equal to summation I, then you want to write your AII as some number, then it's this sum. You can take this sandwich of A between you can take the sandwich of A between two computational basis vector. Okay, so trace has this property. So partial trace has similar properties. So you can show that from here, quite easy to show that if you only do trace on the B part, then this summation on I, then you are only summing. Then this sandwich with I, then you are sandwiching with I on B, I on the Hilbert space of B. Okay, so you can do this summation I, and you have identity tensor this I bra times your rho A B, then identity tensor your I cat. This will be another way to express partial trace. Okay. And also, it says partial trace because you can go from partial trace to full trace. Okay, so if you take I forgot to replace with rho AB here. Okay, so you have rho AB, and you can trace rho A to become matrix of B and trace B. And I guess technically I don't need this B here, and I don't need this A here because it's matrix is already a matrix with only one register. Okay, and anyway, so you can trace A first, then trace the B part, or trace B first, then trace the A part. So here this is a bit tricky. I guess you can either do this or not, but this is kind of the full trace. Okay, so parentheses. Okay, and anyway, you can do this in any order, and that will be same as the full trace. So you trace out everything. Okay, and so hopefully those two properties give you more idea about what's a partial trace. Okay. Any questions so far? If not, okay, then now let's try to finish the proof. The proof is really longer than I thought. Okay, and finish the proof about reduced density matrix. Give you the same measurement outcome. Okay, so we have a setup. So we have a measurement mi set of whatever generalized measurement on C7A, and we have joint state rho AB. So let's think about we have some A, some B. And let's do some measurement with M here, okay? With M, and it's a measurement, and we want to say what's the outcome. And there will be outcome probability and the post-measurement state. And remember from our postulate of quantum mechanics on composite system. So doing this measurement on system means that we are doing this MI tensor identity, this set on system on the full system on AB. Okay. And yeah, so let's go to the density matrix formulation. So probability of outcome I want to trace of these measurement operators and we train with US state. So MI tensor identity rho AB, MI dagger tensor identity rho AB. And now let's try to work this out. So then we use the second property to move this front. And both the second part is identity, so this is just MI dagger and MI tensor identity on rho AB. Okay. And then now let's try to use the break this trace into two partial trace because let's write the end result here. So the end result is we want this equal to trace MI. Okay, that's one less MI dagger MI. And rho A, okay, and where rho A is you do partial trace on rho AB. Okay, you want this thing to give you the measurement probability of the same thing you do on the whole state. We want to say this rho A tells us the measurement probability when we do a measurement on system A. Okay, so you don't need to go to the full rho AB. Okay, so we have this thing. And then we have, let's see, so we want to do trace B first, so this thing is basically trace A, right? So we have a trace A on outside, so trace A, and so this trace A will not be touched again. And then we have a trace B, and this thing, and we have MI dagger, MI tensor identity, and rho AB. Okay, now we need to be careful about our parentheses. So the outer parentheses, let's keep it bracket, and then we have trace B parentheses here. Okay, so this whole thing inside trace B. And let's see, can we do this? So then we have so trace A will not be touched, it's outside, very long. And trace B, I think I want to do the identity thing. So this becomes the summation I. And let's do this slow, identity tensor I bra. And this thing MI dagger MI tensor identity. And oh, this parenthesis is too small because we have a lot of terms here. And identity, no, and here we have this thing here, rho AB, and identity tensor I cat. Okay, and this whole thing. And so we are almost here. So now we see that this summation thing. Okay, there are many steps, but let's try to describe the state a little bit. So first is that those two terms commute. Okay? So here we need to use that we have some identity here. Okay? So those two terms should commute because we have identity here and identity here. So identity commute with this MI dagger MI, and identity can commute with this I bra. Okay? So these two terms will commute. So we can change their order, and then we see that. Oh, sorry. I should. Sorry. It's a bit funny. This I and this I are different, so I should use a different. Let's say it's a J here. Okay, I should use a different dummy variable. J here and J here and a J here. Okay. And so these two terms commute. These two terms commute, and this thing doesn't depend on J. So I can pull by linearity of I guess matrix summation. So I can pull this thing outside of the summation. So this thing is equal to. I need one more line here. trace A, and then this mi term, mi dagger mi. Wait, can I redo this? Sorry. This commute. This is a bit harder. So, I guess I need a HWA slide. Okay. So this commuter doesn't really commute because we have let me see if I can have a HWA space here. Okay. Okay, let's do this thing. Okay. We have something very complicated here, but let's try to be slow and careful. So we have I tensor and this broad J and times okay, we have mi dagger mi. Let's just call the okay, mi dagger mi and tensor identity, and this thing equal to mi dagger mi tensor jkit. Okay, this is just we do multiplication. So each each slot just multiply itself. So identity times this equal to this thing, and identity times this thing equal to this thing. And okay, and so this is a little change here. So if you want to break this thing, it equal to mi dagger mi tensor. Now we change the dimension because this is a broad vector, so it's not square matrix. So we commute, we don't get the identity. We get the identity of one dimension, so it's a tensor 1. And here we have, so this 1 is just 1 by 1. And then here we have I tensor J. Okay, and so let's go back here. Then we will have trace A, and so this thing out, it become mi dagger mi, and tensor 1, which is nothing. Okay, and times summation J, and all those things, the partial trace thing. Tensor J and row AB and I tensor J. Okay, and yeah, so now you will see that this part so this part will become row A tensor 1. And this thing is mi dagger mi tensor 1. So then the second register all become 1. So we can go throw away the second register. So this becomes this trace A mi dagger mi row A. Okay. So want to be careful about this. Is actually a bit complicated. And I think this is the measurement probability. And you can also check the post measurement stage to also give you the same thing. Okay, and yeah, I will correct this right up to HO type form, but for now this is HO proof, which I guess let me say something bad about textbook. So textbook just said this is clearly true with one sentence, and so I look it up and I find out it's you feel it's true, but you want to be careful, then this is quite a bit of proof here. So this is a clear true proof of the partial trace having the same probability. Yeah, so textbook just says that this is equal to this. This is obviously true, but yeah, you need to be careful that there are some middle steps. Okay. Any questions so far about all these partial truth trace rules? If not, and then let's go back to classical computation. Okay. So classical computation is here. Okay. And I guess classical computation will also missing something. Okay. And so let's delve back a little bit about classical computation. So first thing we want to talk about classical computation is we study. I guess computer science there are many different parts, but in this course we focus mainly on computation, and computation is about algorithms. So we design algorithms to do computation, and so we should really ask ourselves first what is an algorithm. Okay, so so algorithm kind of feel like this kind of thing. So it's a set of instructions that they will solve some problem, so one problem. So an algorithm will solve one problem, and now the thing about algorithm is that they can handle different input. Okay, and so algorithm is a set of instructions that let you solve the problem with different inputs. And so, for example, there is this addition algorithm that this is probably the first algorithm you learn in your life. So it tells you how to do addition. You have this 3 plus 2 plus 3, 4 plus 5, etc. And then when you get more bits, there you get a longer bit input. Then there is extra thing you need to deal with your algorithm. You need to do the carry bit and to do your addition, etc. But you have algorithm that you think you can handle the input of any length. Okay? This is what you learn in elementary school. And so this is I guess the essential part of algorithm is that the inputs we always think it can be arbitrarily long or it can be infinitely long. Okay? And so to design an algorithm, you actually need to do something very weird. We need to have a finite instruction. So we don't really want our algorithm, the description is infinitely long. It's very hard to keep up. Okay? So algorithm is something that with a finite size that do infinitely many things. Okay? It's a finite instruction set that let you answer a question with infinitely many different inputs. Okay? And as we say, the really tricky or essential part of algorithm is a finite versus an infinite difference. And so this better motivated why we want to have a Turing machine. Okay? So people think very hard how we mathematically describe what is an algorithm. And so in the end, people find out that Turing machine is a very nice description. Okay? So once again, so we already talked about this last time. So we have the Turing machine. It has some finite part. It has a finite description program and some finite internal memory, finite state control, and we have this infinitely many long tape. Okay. So this head part is a finite part of algorithm. Then we have this infinitely long input and output tape. And the tape is a really interesting part of a Turing machine because it's, as we say, it's infinitely long, and it serves a kind of a three purpose. So it serves as where you have input and where you have output, and also you can use it as a memory, as input in computation. Okay? So designing a Turing machine algorithm really do a lot. You need to be careful about how you use tape. And also maybe digression a little bit, so people think about models of a Turing machine with different type of tape. So how we do tape here is we have the simplest possible tape is one direction tape with infinitely long. So there is some starting position and infinitely long other direction. And you can think about your tape is two-way infinite, or you can even have multiple tapes. And but in the end, that don't give you much more computational power. You can do a little bit more, but it's equivalent to just this simplest possible Turing machine with some overhead. Okay, And yeah, so Turing machine is a way that let you capture an algorithm where you have finite part that deal with infinitely inputs. Okay, and we go to circuit model. So I guess then we need to say something funny. Okay, then we go to circuit model. Now it's a bit tricky. So circuit model, we have a fixed circuit that have some fixed input size and fixed output size here. Okay, so a circuit will describe a fixed size function, so it will describe some fixed input and fixed output. Okay. And theoretically, technically, how you use circuit model to describe a full algorithm is you basically need to wrap up back to your Turing machine. Okay? Because then you want to say we need some finite description to describe your circuit of all different sizes. Okay, and I guess that's we should have it somewhere. No, we don't have it. Okay. Yeah, I guess we can do the extra slide later. Okay, but a thing to think about is how you describe a circuit with different sizes. Okay, circuit. Different sizes. Sorry. Okay. Yeah. So when we write our algorithm in circuit model, so circuit model is quite direct. It's very related to physics. How you do physical design of your actual computer. So you can think about you put a gate here, a gate there, and how you wire up your whole circuit. And but back to theoretical, we still have this infinite versus finite description thing. Okay, so we need a finite description to say how we design our circuit of all different input and output. Okay? And so this is actually a problem that with a net that's called uniformity. Okay. Okay. So okay. So this is called uniformity. How you describe all the circuit with different size. And in the end, if you want to do this very theoretical, the way is so how you do this, you cannot go back to circuit model because circuit always have a finite input and output. So actually, how people theoretically define it is they want to say your circuit is uniform if the description of your circuit can be described by a Turing machine. Okay. So really, if you want to go for theoretical, the basis of all your algorithm always come back to Turing machine. Okay. So yeah, so that's something to note. Okay. This is a uniformity. So this is something nice to know, but in this course we will not be too careful about being uniform because all the algorithm we describe has quite straightforward description about how you put your gates, and it's quite obvious that all our circuits are uniform. Okay. But yeah, if you want to be careful, you need to check that your circuit is generated uniformly. That means that it can be described by some Turing machine. Okay. Yeah, so that's a circuit model, and once again, our circuit model has lots of different gates. We have this AND gate, OR gate, NOT gate, etc. We can string together our circuits to from a universal set, and that will give us some Boolean function, calculate some Boolean function. And I guess more generally, we can compute the function of many input and many bits input and many bits output. But a lot of time we'll focus on Boolean functions because, just because they are simpler. It's a 1-bit output. Okay. If okay, then let's go to the part that we are actually scheduled to talk about, and that's about symptotic notation. And I guess this is still related back to our finite versus infinite. Okay, so we want to describe our algorithm as something that has possibly infinitely many long output. and then infinitely many long, sorry, not infinitely more output, more like infinitely long input. Okay? So we want to see that when our input get longer and longer, how our algorithm perform. Okay, and so this is where we come to this symplectic notation. So we want to see how the resource use in our algorithm grow when the input grows, okay, input size grow. Okay. And yeah, so now let's go to the dirty math detail of our symplectic notation. So I think there are 5 notation, and 3 of them are most used. I guess the big O is mostly used, and also the omega, big omega, and big theta are very important. And then sometimes you will see the small and the small omega. Okay. And then today we have time, so let's go slowly through how they are actually defined. So first is this big O notation, and so these notation are related to 2 functions. So there is something that there are 2 functions that scale with your inputs. This n is mathematically this is the scaling parameter, but we can just think about its input size. So n is maybe an integer. And anyway, so we have this f function and a g function. And we say f is O of g, so f is related to g by this big O if these following things satisfy. So this is a really calculus description. So we say if there exists some constant c and some constant n0 such that for n bigger than this n0, then f of 0 will be less or equal to this constant c times your g of n. Okay. And yeah. And to make things a bit simple, we assume that they are both greater or equal to 0. So everything is positive. Yeah. Okay, so this is a big O notation. And I get a bit of criticize here. And so something funny about this big O notation is you see that this notation is really about an inequality. So it's f is less or equal to g. But take-home notation here is you need to write the equal sign here. Okay. So yeah, this is a weird convention, but this is how people write things. You say f is big equal to big O of g, basically means f is less equal to g with some constant. Okay. Okay, and yeah, I think in one paper I see people write less or equal here, but that's not standard notation, so try to avoid, I guess. Yeah. And back to what this symplectic notation actually means. It means that so you have some f and g, and we don't care about how they behave when your n is small. So when n is small, they can be anything. But when n is very large, then so this is where this cutoff n0 come from. So after n is bigger than this n0, then f of g will symplectic approach something. So everything after this n0, so from n0 to n to infinity, f should be less equal to g. And but we also don't care about constant factor, so we can have f less than equal to g times some constant factor. So maybe g is actually smaller than f, but f is less than g to some arbitrary constant. And by constant, we mean that this c doesn't depend on n. Okay, so c is just a fixed number that doesn't depend on n. Okay. Any question about definition of big O notation? No. And yeah, so this is big O. And then if we know big O, then big omega is quite easy. So big omega is just a reverse of big O, is lower bound. Okay, so we say f equal to big omega of g if we still have the same c and n0, and we want that f is greater or equal to c times g of n when n is greater than n0 and for some c. Okay, so this is just a reverse. So we say we think g is a lower bound of f because when n is big enough, f is always greater or equal to g. So lower bound and upper bound. Okay, and then finally, oh, I guess not finally. Excuse me. Not finally, but the next we have the big theta notation. And big theta is basically just big O and big omega together. So means that so we have f equal to theta of g of n. That means that when excuse me, when n is big enough, then f is basically equal to g up to some constant factor difference, constant factor gap. So we have some c1 and some c2, and f is between c1g and c2g. So if you like, f is maybe something in the middle like this, and there's c1g and c2g. Okay, so those are sympathetic notations. And yeah, as we say here, we have equal sign, so don't write f of n is greater or equal to omega of g. Although this is what they feel is true, but it is not the syntax, the standard syntax. Okay. And yeah, so those three are most commonly used. And then there are two less commonly used notation. And small omega is just you change the greater equal to, the smaller equal to, or the bigger equal to smaller or greater. Okay. So you really want this thing to be less than this thing. Okay. So f of n is I guess also a different part. Okay. But we want f of n to be, I guess let's talk about small a little more. Okay. So this is smaller equal to, and also we change the quantifier here. Okay, so this is also important. I should be red. Okay, yes. So this is very important here. So let's also circle this. Okay, so we want that for constant c, f is less than c times g of n. Whereas before we have is this constant. Okay, so we cannot just pick some big constant c and say, well, f is less equal to g. And we want for constant c greater or equal to 0, f of n is less than g of n. So we want f of n to really grow slower than g of n. That's the idea. Okay. And yeah, so here we have an example. So f of n equal to maybe 2 times n, and g of n equal to n, and and so we can pick if c equal to 2, then say if c so f of n is less than equal to 2 times g of n, and so if c equal to 3, then this is satisfied. But for c equal to 1, we don't have f of n less than g of n, so we have that 2n is not small of n, because 2n don't really grow slower than n. Okay, so this thing is for this is the small notation, and I guess an example that so why do people want this really weird notation? The most time I will see this is people want to do this thing. Okay. Okay, so it's this kind of thing that people want to do. So the thing you see mostly inside small is 1. Okay, so people want to say something is growing smaller than constant means something is approaching 0. Okay, so this small of 1 is some nice notation. It's something that grows slower than constant means that when n goes to infinity, your thing is less than any constant, and basically means this thing goes to 0. This is, I guess, a computer science way to say that your limit of your thing is 0. Okay. So, sorry, let me pick this up. So yeah, I think this fixes the calculus. Why is this thing weird? Okay. So I think this actually fit the calculus definition totally. Okay. Yeah. So this thing here. So we say f of n equal to small o1, and that means limit of n equal to infinity, f of n equal to 0. And I guess here you see there is some advantage in computer science notation, because there is just less writing here. Okay, so yeah, limit of n goes to infinity. f of n equal to 0, just we are writing this as f of n equal to small 1. Okay. And then there's a different thing. So then there's the other way of the small notation is the small omega notation. So this is the other way of the lower bound. So we mean f of n equal to small omega of g of n means that as n go to infinity, f of n is growing faster than g of n. So we have also for one constant c here, and f of n needs to be greater or equal to c g of n. Okay. And yeah, I guess similar to the small. So small omega is also can be also mostly used when we have small omega of 1. So f of n equal to small omega of 1. Now this thing in terms of calculus, this means that the limit n go to infinity, f of n equal to infinity. So it's greater or equal to any other constant. Okay. Yeah. So yeah. So this is why people like a small and a small omega, because it's a nice way to describe limiting of your function go to 0 and infinity. But obviously you can also put different things inside. And yeah, so I guess here we have an example of all the different things. So here we have n squared is a small of n cubed, because as n goes to infinity, n cubed is just growing faster than n squared. Okay. And we have n log n is a small omega of n, because we have a extra log n factor here, which goes to infinity as n goes to infinity. And also log n is omega of 1. Although this thing grows very slow, it still go to infinity as n go to infinity. Okay. And we also have either examples. We have examples of big O and big omega. So we have 2n squared is order n squared. Okay. So yeah, I guess it's the example that's here. And also n cubed log n divided by 4 is omega n cubed log n. And well, basically this thing is almost the same as this thing, but it's divided by 4, so it's this divided by 4 constant we don't really care in our big O notations. Okay. And then we have dirty example in more detail here. Okay. So we have that we want to show this a very easy thing. Okay. So if you want to show this in full detail, then you need to write all the exists and find out all the exists constant, etc. So we have 2n squared equal to order n squared. So this is really like the the proof you want to write in your basic calculus course. So we have f of n equal to 2n squared and g of n equal to this n squared. And then we want to find the constant c and n0 such that for n greater than n0, f of n is less than cg of n. So the c and the n0 we found is c equal to 3 and n0 equal to 1. And let's see how it works out. So f of n equal to 2n squared, and 3g of n is 3n squared. Okay. And then here we see n0 is also important, because when n less than 0, n squared, I guess sorry, n0 is not important here. So 2n squared is always less than or equal to 3n cubed, 3n squared. And here we just want whatever n0 that's not 0. Okay. And yeah, 2 less than 3, so 2n squared less than 3n squared. And yeah, so this complete the proof here. Okay. And here we have a bit, I guess this is a bit more important than you think. Okay. So yeah, so if you always go to this calculus, if you always go to this calculus definition, then it's just a lot of write up and a calculation to do. And so usually what people do is we just do the cheat sheet here. Okay. And so there is a cheat sheet of the ordering of what the function is bigger or smaller than other function. Okay. And so we have the hierarchy here. So we have constants smaller than log, and the log is smaller than linear function, and the linear function is smaller than exponential function, and the exponential function is smaller than factorial. Okay. And so when you write a big O notation and you add many things together, you just need to pick the highest thing, etc. Okay. And here we have so here we have a little bit of insight, I guess, between log and n. I guess the cheat sheet can be longer. Okay, so in the middle here, so between log n and n, there are polylog n. Okay, so you have a polynomial over log n is between log n and n, and between n and 2 to n, there is also polynomial. Okay, so you have a polynomial of n for some constant constant degree is always less than 2 to n. Okay. So yeah, this is a cheat sheet for asymptotic notation. Okay. Okay, so we can have an example here. So example, so n plus log n to the cube equal to let's just like theta over n, something like this. Yeah. So the lower order part, if you are adding with the higher order part, then you can just ignore it. Okay. We have 7 minutes. It's a bit tricky. Let's see. For more, let's start a little bit on the next idea, and but we'll start again from here. Yeah. And let's go over a bit of overview of next time. So next time we are going to describe problems. Okay, and so I guess this really wrap up back to our algorithm. So we say algorithm is an instruction to solve a different problem. So what is a problem with infinitely many different inputs? Okay, so we need a finite instruction. So algorithm is something with a finite instruction to solve problem. But the problem itself we also want a finite description. So how we have a finite description? But I guess I don't care too much about finite description problem. But anyway, we need to describe a problem with infinitely many different inputs. Okay. And in particular, so problem means is something with answer. So a problem has different input and different outputs. Okay. And yeah, so this comes to this formal language and the decision problem. Okay. So decision problem is really problems that they ask you to calculate Boolean functions. Okay. So decision problem are problem with two answers. There is a yes answer or no answer. Okay. So any input you will have some yes answer or no answer. Okay. So they correspond to Boolean functions. Okay. So you want to calculate some Boolean function. Okay. And yeah, maybe there is an example. So example of a problem with a yes or no input is you give a number and give you an integer and ask you whether it's a prime number. Okay, so is 67 a prime number or not? And the answer is yes. Okay. And then we have the formal language is a very formal way to describe what's a problem. Okay. And so problems really calculate the function, so there is input and output. Right? Okay, so problem has input, and so every input corresponds to some output. And formal language is basically a way to label your input because we are on decision problem. So your input can only be labeled with yes. It either has a yes as the output or no as the output. Okay. And so formal language just mark all the, I think it's all the yes input. Okay. So and also we so we have input over this subset over this set of all possible inputs. So input we have some alphabet, and so alphabet and this sigma. The alphabet sigma is just a collection of symbols. So maybe you have A, B, C, D, your alphabet. And then the set sigma star means alphabet with a string of those alphabet with arbitrary length. Okay, and yeah. So we have this weird sigma star notation, means a string of arbitrary length, where this string has string is composed of those alphabet symbols. Okay. And then what's a language is a subset. So subset of the sigma star. So it's all the string, some string of arbitrary length, and yeah. So it's just a subset. So we have alphabet being arbitrary input, and we mark some subset of them with output being yes. So that's the idea of this formal language. Yeah, it's quite complicated. And I guess here is an example. So we can have our alphabet. So mostly the most often choose alphabet is well, not the English alphabet. English alphabet is A to Z. The most often choose alphabet in computer science is 0 or 1. We like our bit string. So we can have our alphabet is 0 and 1, and the sigma star will be just all possible bit string of all possible number. Okay? And then we can have a language that represent every even number. So it's basically just all possible all possible string that end with a 0. Okay? So it's either 0 or 1 0 or 1 0 0 or 1 1 0. And yeah, and I guess if it is alphabet, then we can also have also 0 0 is also inside the alphabet, and is also inside this set, and we can have 0 0 0, and yeah, etc. And yeah, here is a bit confusing because we have multiple representation of 0 if we are talking about numbers. But if we talk about the set sigma to a start, then we also include those string of multiple zeros, etc. Okay. And I guess we can have another alphabet. Say we just have alphabet that correspond have a string of all 0. Okay, so we can also think about all these alphabet. It's just all 0 strings of different lengths, etc. And yeah, and this thing actually has a name. I think this is called unary input. Okay, just strings of all those. I'm not too sure, but I think it's this name. Okay. Yeah, so this is another example of alphabet. That's just all zeros, etc. Okay, and yeah, so this is the description of formal language, and we are going to use this weird language to describe problems a little bit. But I think mostly this is this is more for your culture. So because if you read more theoretical papers, you will see this kind of notation. But really, this is just a very formal way to describe a decision problem. Decision problem is a function that give you 1 bit output, and they want to have a very formal description, and you will see some descriptions like this. Okay. And yeah, so I think it's time for class, and we will talk more about decision problems and the complexities next time. And I think we'll also start the quantum circuits in next class. Okay. Yeah, so see you next time. I will try to upload the edited slides as soon as possible. Yeah.